In this video, we're going to explore in much more detail exactly how two atoms will come together in a bond. We're going to be looking at something we call valence bond theory and investigating what happens when the orbitals on certain atoms overlap in order to form these bonds. We're going to define two different types of bonds here. We're going to have sigma bonds, which overlap along the internuclear axis. Consider that to be basically a line connecting two nuclei directly together. We're also going to look at what we call pi bonds. Pi bonds overlap above and below this internuclear axis. And so, for instance, we can see here what a sigma bond would look like, in which the electrons are going to simply occupy the space in between the two nuclei. This would be as opposed to a pi bond, in which electrons now occupy space above and below the two nuclei of the atoms. If we only have one sigma bond that exists in a molecule, we would consider that to be a single bond. Double bonding occurs when we have a sigma bond and a pi bond in a molecule. For instance, if we look at a double bond between carbon and oxygen, one of those bonds is a sigma bond, the other is a pi bond. Looking at some examples of different ways here that sigma bonds can form, we see in our first example just an H2 molecule. That sigma bond is going to form when the two different s orbitals are able to overlap. Here we have an HF bond in which the s orbital from hydrogen will now overlap with our p orbital from fluorine in order to create our sigma bond. In F2, our two p orbitals from each of the fluorine overlap in order to create our sigma bond between the two of them. This slide just includes some of the various terminology that we'll be using throughout this video. If you're not sure or forget what a term means, simply refer back to here to remind yourself of some of these different definitions. In many cases, the bonding of molecules cannot be explained by the simple overlaps that we showed earlier, and the geometries of certain molecules also cannot be explained by those overlaps. In order to see exactly what's going on, we have to look at what we call the hybridization of orbitals. In other words, taking s and p and even d orbitals and mixing them up in order to create new hybrid orbitals which will participate in bonding. For instance, when we look at a simple molecule like methane, CH4, our VSEPR theory predicts that we are going to have equal bond angles of 109.5 degrees. However, those angles are simply not able to be achieved if we consider the s and the three different p orbitals of the central carbon atom. In other words, if our orbitals remain as we have studied them before, we cannot form the molecule as we know it. So something else must be going on. And so consider a carbon atom as we've talked about it so far. We have our 4 valence electrons, and so we've said that our electron configuration for carbon is going to end in 2s2, 2p2. And we see that drawn out here with our orbital filling diagram. We see our 2s2 electrons and our 2p2 following Hund's rule with one electron in one p orbital and one electron in another p orbital. And so this is what carbon might look like if we have just a lone carbon atom. However, in order to form bonds, what is now going to occur is that this s orbital is going to mix with these 3 different p orbitals in order to create 4 different hybridized orbitals. And so we see that here. Our 1s orbital and our 3 different p orbitals now mix together to create 4 sp3 hybrid orbitals. Our electrons that we had in our s and our p orbital, our 4 valence electrons, are then able to populate those 4 different sp3 orbitals, one in each orbital. And now our 4 different hydrogen atoms can come in with their electrons in the s orbitals and overlap now with the hybridized sp3 orbital in order to create a covalent bond holding the molecule together. And so we have what we would call an sp3 overlap, which will create our sigma bond between each carbon and hydrogen. And so here we just see that depicted with our various orbital shapes. We see on top our unhybridized carbon atom with our 2 electrons in s2 and our 2 electrons here, 2p2. Here's our s orbital, our 1, 2, 3p orbitals, and then our hybridized sp3s with these various shapes. We have now 4 hybridized sp3 orbitals which are able to bond with other atoms. And since we now have 4 equal sp3 hybrid orbitals, they must spread out in order to form the classic tetrahedral shape around the central atom in order to minimize that repulsion. And so any atom that has an sp3 hybridization will exhibit the tetrahedral electron domain geometry. And so here we see the case of ammonia, NH3. Here's our Lewis structure. We have 1, 2, 3, 4 electron domains. We see it here drawn out with a Vesper shape. And so we still have our 1, 2, 3, 4 electron domains for a tetrahedral electron domain geometry. 1, 2, 3 of those are bonding, making a trigonal pyramidal Vesper shape. And so those s and p orbitals of nitrogen will hybridize to form 4 sp3 orbitals. 1, 2, 3 of those will be taken up with bonding to hydrogen atoms. The 4th hybrid orbital is where our lone pair will reside. And we see the same with water. Our oxygen atom must have a sp3 hybridization in order to form our tetrahedral electron domain geometry. And so 2 of those sp3 hybrid orbitals will be used to bond to hydrogen atoms. The other 2 will be used for lone pairs. And so when the central atom in a molecule has a combination of 4 sigma bonds and lone pairs, then the hybridization of that central atom will be sp3. And so to look at another example, maybe carbon tetrachloride. We see that we have 1, 2, 3, 4 sigma bonds. And so those 4 sigma bonds must be residing in sp3 hybrid orbitals around our carbon atom. And so we need, again, 4 sigma bonds that will come, and those hybrid orbitals will come from taking 1 s orbital and 3 p's for an sp3 hybridized orbital set. Let's take a look at, however, at our bonding in BF3. In BF3, we're only able to form 3 bonds around our central boron atom. And so in that case, when a hybrid orbital forms, we're going to form that hybrid orbital from 1 s orbital, and now we're only going to take 1, 2 of our p orbitals to form 1, 2, 3 sp2 hybrid orbitals. And then we still have a remaining 2p orbital that has not been hybridized. Again, we've instead formed 3 sp2 hybrid orbitals. So we have 1 p orbital left over. When we form 3 sp2 hybrid orbitals, we will always form sp2 orbitals whenever we need a combination of 3 sigma bonds and or lone pairs. And here is just a picture of that once again, looking at our various orbital shapes. We have our unhybridized s and 3p orbitals. When we hybridize, we're going to take the s orbital, and now we're only going to take 2 of our p orbitals in order to form 1, 2, 3 sp2 hybridized orbitals, and the remaining p orbital that we have not hybridized. And so we can see here what the trigonoplanar bonding would look like in BF3. We see that we have 3 sp2 hybridized orbitals surrounding our boron atom. The fluorine atoms are then able to bond with those sp2s in what we would call a p sp2 overlap in order to form those sigma bonds. Now recall that when we form an sp2 hybrid orbital, we're only using 2 of the p orbitals. Our leftover p orbital that we have not used is also capable now of forming a pi bond with another atom that may have a half-filled p orbital. And so each of the sp2 orbitals can form what we would call an end-on overlap. In other words, we might have an sp2 orbital coming out like this, and then possibly a p orbital like this in order to form a bond, and this would be our sigma bond. We could have, however, also a case where we have 2 p orbitals in a sideways overlap, and we're now going to form a bond like this between the two. That then will result in our pi bond. So let's take a look at what that looks like using an orbital filling diagram. And so here we're looking at an example of C2H4, in which we have a double bond in between our 2 carbon atoms. And so each carbon we can see is forming 1, 2, 3 sigma bonds and 1 pi bond. Recall that a double bond consists of 1 sigma and 1 pi bond. And so each carbon is forming 3 sigmas and 1 pi. And so since we need only 3 sigma bonds, our carbon is going to sp2 hybridize to form 1, 2, 3 sigma bonds, and is now going to have a leftover unhybridized p orbital, which will be capable of then forming our pi bond, which is the second half of our double bond. And so we can see that illustrated here. If we're looking at our C2H4 molecule, we can see here just all 3 of our sigma bonds. We have our 1, 2, 3 sp2 hybrid orbitals from this carbon. One of those is forming our CH bond here, another is forming our CH bond here, and the other forms our carbon-carbon sigma bond with one of the sp2s from our other carbon. The unhybridized p orbitals are then able to form our pi bond above and below the plane of the molecule. Let's take a look at what that looks like again with an illustration here. And so around each carbon, we're going to have 3 hybridized sp2 orbitals. And so let's draw those in. We have one sp2 orbital here. We have another sp2 orbital here. And a third sp2 orbital right here. One of those sp2s is able to form our bond here with hydrogen's s orbital. One forms a bond here with the other hydrogen's s orbital. And the other one is able to contribute to a sigma bond to the other carbon. Now let's just draw in quickly the other carbon's orbitals. And we can see that our sigma bond between the 2 carbons will form right here. Now remember, we still have an unhybridized p orbital around each carbon. And so we're going to have electrons from each carbon in these unhybridized p orbitals, and that will form an overlap above and below the molecule, making up our pi bond. And so in each, we've got our 3 sp2 hybridized orbitals in red, and our p orbitals giving us our pi bond in green. The blue represents the s orbital from each hydrogen interacting with the red sp2s to form our CH sigma bonds. Another instance where we will see sp2 hybridized orbitals is with a compound like acetone. Our carbon atom in the center will form 3 sp2 hybrid orbitals, shown here in red. Our carbons on the end will form sp3 orbitals, providing a sigma overlap in order to form sigma bonds between those carbons. Note that our oxygen atom also has 3 electron domains, and so that will form 3 sp2 hybrid orbitals as well. One of those will provide our sigma overlap between the carbon and oxygen. The other 2 will hold the lone pairs on oxygen. Now remember that we still have a p orbital in our carbon that has not been hybridized. We also have a p orbital in our hydrogen that has not been hybridized. This will allow for pi bonding to the sides of this molecule. And so between the carbon and the oxygen, we have 1 sigma bond and 1 pi bond, creating our double bond between the 2. Lastly, if we only have 2 sigma bonds that need to form, then that atom will take the 1s orbital and will only take 1 of our p orbitals in order to form 2 sp hybridized orbitals. And now we'll have 2 p orbitals left over. A good example of this is when acetylene forms, C2H2, which will have a triple bond between the 2 carbon atoms. And so we can see that we need only 2 sigma bonds for each carbon, and the other 2 bonds of our triple bond will be made up of 2 pi bonds. And so a triple bond is made up of one sigma bond and two pi bonds. The two sp2 orbitals can hold either sigma bonds or lone pairs, depending on the molecule. The p unhybridized orbitals are then able to form our two separate pi bonds in a triple bond. And we can see an overall picture of what that looks like here. And so in yellow, here in the middle, we have our two sp2 hybridized carbon atoms. And so that is the basis of our sigma bond in between the two carbons, and also our overlap for our sigma bonds between carbon and hydrogen. We also have two different sets of pi bonds in this molecule. We have one here that is both above and below the plane of our molecule, shown here. We also have a pi bond that is located on both sides of the molecule. And so again, let's just look at a bigger picture of that here, drawn in conjunction with our Lewis structure. So on each carbon, we have an sp2 hybridization, giving us the ability to form sigma bonds with our hydrogen atoms, and also a sigma bond between the two carbon atoms. And so since we have formed sp2 hybrid orbitals, recall that what that leaves us with are two p orbitals that are still unhybridized around each carbon. And so let's draw those in as well. Maybe we have one p orbital oriented like this around each carbon. And let's say we have another one that is oriented like this around each carbon. So there's two p orbitals that are still available, and those two p orbitals can now participate in pi bonding. We'll have a pi bond between these two, and we can form another pi bond between these two. And so that now gives us our one sigma bond between the two carbon atoms, and it also gives us our two pi bonds between the two. So one sigma bond and two pi's for our overall triple bond between our two carbon atoms. Some other examples of sp hybridization could involve triple bonds with nitrogen. Each of the nitrogens in N2 will sp2 hybridize. If we have our cyanide polyatomic ion, a triple bond between carbon and nitrogen, we will have sp hybridization on both the carbon and the nitrogen atoms. And so if we're looking at our relationship between hybridization and molecular shape, we see that sp hybridization leads to a linear electron domain geometry. And so in this video, we've explored sp, sp2, and sp3 hybridization. I know this is not easy, and I know this is not necessarily intuitive stuff. Go back over this video as many times as you need, look at some example problems, and try to make sense of how various orbitals will hybridize in order to form the hybrid orbitals they need to in order to bond. Please feel free to come see me if you need some extra help looking at various hybridizations. I hope this has been helpful.